Welcome back to gases. In part 4 of this unit, we're going to be looking at molar volume and the ideal gas law. This is going to be awesome. Let's go. So first of all, molar volume. That's the volume of a mole. Because Avogadro's law says equal volumes of gases at the same temperature and pressure have the same number of molecules, if that temperature and pressure happen to be STP, 0 Celsius and 1 atmosphere, the volume of 1 mole is always going to be 22.4 liters, no matter what kind of gas it is. So it could be helium. 1 mole of helium is going to have a volume of 22.4 liters. 1 mole of oxygen is going to have a volume of 22.4 liters. 1 mole of carbon dioxide is going to have a volume of 22.4 liters. Notice that their masses will not be the same because a mole of helium weighs only 4 and a mole of carbon dioxide will weigh 44. But they will have the same number of moles, the same volume, the same temperature, the same pressure, even though the masses will be different. So let's just work a problem. At STP, because we know what the volume of a mole of gas is at STP, find the density. Density is equal to mass divided by volume. And so if we were looking for the mass of a mole and the volume of a mole, for oxygen, that'd be 32 grams. And at STP, that'd be 22.4 liters. 32 grams in 1 mole, 22.4 liters in 1 mole. So my density is 32 divided by 22.4, 1.43. And since the moles cancel, grams per liter. Notice the unit for density for gases tends to be grams per liter, not milliliter, because gases will take up a whole lot more space, so we need a larger volume unit. Okay, what about acetylene? Acetylene has a density of 1.16 grams per liter. D equals, at STP, find the GMM of acetylene. That's the molar mass of acetylene. So if we've got density is equal to mass over volume, and if we're looking for the mass of a mole, the volume of a mole, or the mass of a liter, the volume of a liter, we've got 1.16 grams per liter. I don't know the mass of a mole, but I do know 22.4 liters is the volume of a mole. So I can use density times volume is equal to mass. 1.16 times 22.4 is 26. And notice that my liters will cancel out, so my units are grams per mole, which is the GMM of acetylene. All right, if 0.50 grams of a gas occupies a volume of 200 milliliters, under STP conditions, what's the GMM of the gas? Well, I know if it's STP conditions, then 22.4 is the volume of 1 mole. So if I'm looking for the GMM, I'm looking for the mass of 1 mole. And so then my 0.5 grams and 200 milliliters will relate. So let's go ahead and make those relate. First of all, 200 milliliters is 0.2 liters. So we can kind of set up direct proportion. 0.5 grams to, let's try that nicer, 0.2 liters as x grams is to 22.4 liters. So we're setting up a proportion. Alternately, you could find the density by 0.5 divided by 0.2, and then set that up equals to x over 22.4. So we'll cross multiply. 0.5 times 22.4 divided by 0.2. X should equal 56 grams per mole. That is the GMM of this particular gas. So what happens when the gas is not at standard temperature and pressure? The volume will not be 22.4 liters of a mole. So that's where we get the ideal gas law. PV equals nRT. Or you could rearrange it to get molar weight is dRT over P. So I'll talk about that in a second. But first, let's look at this. PV equals nRT. Remember the combined gas law? P1V1 over N1T1 equals P2V2 over N2T2. Well, if you just take out the ones, just PV over NT, notice that that all equals R, which is where the ideal gas law comes from. All of that is a constant. R, the gas law constant, is 0.0821. liters atmospheres per Kelvin mole. Latcomole, 0.0821 latcomole. That's your R. It is a constant. It will always be that number, so you can just memorize that number. And that's why we have to have, from here on out, all volume units in liters, all pressure units in atmospheres, all temperature units in Kelvin, and moles of course, are moles. So now let's look at that second equation. Sometimes it's helpful to be finding molar weight. What's the molar weight of a particular gas? And sometimes densities are given instead of masses or volumes. So this second formula is here to help you out. Here's the idea. Molar weight is the mass per mole of a substance. So essentially that's mass per N. And so you can rearrange that to be, if we say that that was N right there as the moles, you could rearrange that to say that N is equal to mass over molar weight. N is equal to mass over molar weight. So PV equals mass over molar weight times RT. So now let's rearrange that formula for molar weight. So if I multiply both sides by molar weight, I have molar weight is equal to mass RT over PV. So that's essentially multiplied by molar weight and then divided by PV. And then I can take this term, mass over volume, and turn that whole thing into density. So I end up with molar weight is density times RT over P. And so the final idea is, what does a cat say? Cat says, meow. What does a cat do in its garden? Well, a cat puts dirt over its pee. That'll help you remember the formula. Molar weight is dRT over P. Sometimes, alternately, you can use molar weight as mass RT over PV, or for all of these formulas, you could use PV equals nRT and just convert and solve. So these are just a couple of ideas of different formulas that might help you solve for depending on what the question's asking for. Let's look at what this question's asking for. When a sample of carbon dioxide at 21 degrees C and 740 torr has a mass of 22 grams, what volume does it occupy? So we've got temperature, we've got pressure, we've got mass, which is not in PV equals nRT, and we've got volume. And of course, remember that you also have R, because you always have R, 0.0821 latcomole. So it looks to me like I want to solve PV equals nRT. The problem is I need N, and N is not 22 grams, but I can certainly get N from 22 grams because carbon dioxide is CO2, which weighs 44 grams per mole. Then I can say 44 grams per mole. Really, this is 0.50 moles. Also remember all your units that have to match up. The 740 torr can't stay that way. It has to turn into atmospheres. 740 over 760 is 0.974 atmospheres. And then the 21 degrees C can't stay that way. That's also got to change to Kelvin. That's 294 K. Now that I have that, then all I've got is PV equals nRT. Since we're looking for volume, V equals nRT over P. Let's plug in what we have, 0.50 moles times 0.0821 latcomole times temperature, 294 K, divided by pressure, 0.974 moles. Multiply, 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 and divide. Hopefully you're going to get 12.4 liters, and that's your final answer. Let's look at another. A liquid can be decomposed electrically into two gases. In one experiment, one of the gases that was collected had a mass of 1.090 grams, volume of 850 milliliters, pressure of 746 torr, temperature of 25 degrees C, R of 0.0821 lacmol. What is the formula weight, or GMM? So this time, instead of using PV equals nRT, which is totally fine, you can use that, you can convert and plug it in, and that's okay. But since I have a formula for GMM, or molar weight, I'm just going to go ahead and use that formula for GMM, or molar weight. And also, since I'm not given density, I'm given mass and volume, I'm going to use the one that has mass and volume in it. So that's molar weight is equal to mass RT over VP. Remember, this term here is like D, so that'd be DRT over P. So really, all I have to do is plug numbers in. Just plug everything in exactly as it is. My mass is 1.09 grams. R is 0.0821 lacmol. T is 25 degrees C. 25 degrees C? Oh no! Say it ain't so. We can't use a Celsius temperature. That's gotta be 298 K. Are there any other units that I left out? Check out the torr. 746 over 760 is equal to 0.982 atmospheres. And the volume, dear, that won't work either. 1,000 milliliters in a liter, 0.85 liters. Once you've got that, make sure that your units all match up and all the units are going to cancel out. You end up with 31.96 grams per mole, which is my GMM of this particular gas. Let's do another one. This time, try it on your own. Pause the video now before you come back and see how I answer it. Okay, hopefully you did that. Since this one's asking for density, I'm going to use that meow is equal to dirt over P. But I want the D part of the dirt, so I'm going to take P times my MW over RT equals density. And that way I can find bent density. I'm just going to plug the numbers in directly as I see them, except make sure your units match like they should. Let's see, pressure is 0.85 atmospheres. Molar weight, since it's oxygen, O2 is 32 grams per mole. R is 0.0821 lacmol. T is 298 K. Multiply, divide, atmospheres cancels. Let's see, moles cancels, kelvins cancels. I'm left with grams per liter, which is a really good density unit. And it is 1.11 grams per liter. Or at least that's what I got. Please make sure you have checked it on your own calculator and make sure it makes sense. One last problem. This time you're calculating the GMM. Do it again on your own. Alright, hopefully you tried it. Take a chance, see what you get. We're looking for the molar weight. We are given the density, so I'll use DRT over P, which is nice. I can just plug things in exactly as they are. Make sure you have changed the Celsius to Kelvin. Make sure you took that 755 and divided it by 760, so you change that to atmospheres. All my other units look good, so I can just plug in 1.14 grams per liter, 0.0821 lacmol. Temperature is 295 K. Pressure is 0.993 atm. So my units, atmospheres will cancel, Kelvin cancels, Liters cancels. I'm left with grams per mole, which is a really good unit for molar weight. And I got 27.8 grams per mole. For all of these problems, I did not round in the middle. I stored that 0.993 number in my calculator instead of rounding it off to actually 0.993. So your answer may end up being a little bit different because of rounding, but as long as it's close to 27.8 or somewhere around 28, you're probably good. Okay, that's molar volume and ideal gas law. We'll see you next time for stoichiometry.